Today, I'm pleased to introduce you Dr. Kosmas Gazeas from the National and Kapodistrian University of Athens in Greece. Dr. Gazeas was born in Kastoria, Greece. He studied physics at the Aristotle University of Thessaloniki, and he got his master thesis and a PhD degree in observational astrophysics from the National and Kapodistrian University of National and Kapodistrian University of Athens. His postdoctoral research in astrophysics was conducted at Harvard Smithsonian Center for Astrophysics in USA, where he worked with the images taken from HST. He worked at the European Space Agency, ESA, in Netherlands, where he specialized in space technology and optics. Dr. Gazeas is now working at Observational Astrophysics at Physics Department. His education and research activities are focused on the study of eclipsing binary stars, primordial asteroid families, supernovae, blazars, black holes, and other exotic objects in our universe. He works in parallel with the astro-seismology on various space technology topics, applied optics, and astronomical instrumentation. In parallel to his research activity, his passion about space exploration led him to participate in the astronaut selection process at ESA in 2008. He managed to be shortlisted among the top 500 candidates in the world. In 2023, the International Astronomical Union named the asteroid 30278 Gazeas after Dr. Kosmas Gazeas, honoring him for his contribution to the study of the most ancient asteroids, as well as for the outreach and public engagement activities relevant to solar system science. His rich research work is reflected on a large number of research and academic assignments on various astronomical subjects, while his interest in public outreach led him to get involved with science communication. During the past years, he gave numerous talks in schools, universities, and other institutes, while he is an active organizing member in Athens Science Festival. He is a member of the International Astronomical Union, the European Astronomical Society, and the Hellenic Astronomical Society. Today, Dr. Gazeas will talk about low-mass contact binaries as proof of stellar merging events. So thank you very much, Dr. Gazeas. The floor is yours.
Thank you very much for the invitation and for this introduction. And thanks everybody for being here today on this seminar talk. As you can see, the topic of my talk is going to be on contact binaries, actually on stellar systems with a common envelope. I will specialize on the low mass regime of the contact binaries, which was something for the first time initiated this summer in July at the European Astronomical Society in Krakow in Poland, when two different groups of people working on the common envelope stars from low mass to the high mass regime merged together in a common session. So this is a talk that was derived after this collaboration between the low mass and the high mass communities, let's say. And I will talk to you about the systems as probes of stellar merging events. The initiative of having such a session, a specialized session at the European Astronomical Society, is that binarity in nature is something very common. We see binary in the universe in all kinds of scales. We can see binary asteroids or even planets or dwarf planets, up to binary stellar system, which is the topic of our talk today, as well as binary galaxies and huge scale objects. So binarity in nature is something very, very common that we see it everywhere. Of course, the gravitational interaction is the driving mechanism of such a configuration to exist. Like photospheric spots, which gives a signature on the light curves. And of course, the low mass contact binaries have members, very low temperature members, with convection zones of photospheric activity, something very commonly observed. And since we have a contact configuration, the mass transfer between the components, as well as the angular momentum transfer and angular momentum loss through the stellar wind, is a common phenomenon that we usually observe. Since we can derive all these physical parameters like the mass, the radii, and the mass transfer between the components, all these physical parameter values and their modulation, the temporal modulation of these parameters can be easily monitored. So the orbital period modulation should be monitored in order to see if the system are trying to expand as a binary object, or they are shrinking their orbit as a merger progenitor. So the orbital period leads towards merging events, and eventually this will lead to a red nova eruption, which is not very commonly observed. The stellar interaction is one of the most basic mechanisms that drives the system. The binarity and the system is not an easy task. Most of the binary systems are observed within a triple or quadruple, in general, multiple systems. Of course, it has to be hierarchical multiple system, otherwise the system will be just chaotic. And the stellar evolution alters the physical parameters across time. So the stars evolve, they expand, they change the mass, they change the radii, all the physical parameters. And however, the evolution is very slow. And what we see right now is just a snapshot of all this long-lasting process. So we don't have to forget that the contact configuration that we see today is the result after giga-years of evolution of probably totally different stars that started in the beginning. All this information that we see observationally today challenge the model, challenge the theoretical models, the physical models. For example, a simple, non-evolving, point-like binary system is well described mathematically. It's the two-body problem that we all know. We actually teach it at school and at the classroom. Evolution in a binary environment is totally different from a single star evolution. We know the single star evolution from main sequence towards the red giant, branch, expansion, planetary nebula, and so on. But within a binary environment, the evolution is totally different. Take a simple example. Take a binary system like the one that I show you here on the bottom right of this slide. If you have the more massive component starting to evolve, starting to expand from the main sequence towards the red giant branch, this expansion will not let the binary star expand forever and become a red giant. From the very first day of the expansion, the excess of the mass, the excess of the photosphere of the star will rapidly transfer to the secondary component. That means that the evolution of the more massive star will slow down. On contrary, the evolution of the less binary star will speed up. Sometimes we have mass ratio reversal. So the most massive star, the more massive star can become the less massive star after several years of process. So the evolution within the binary environment might be even slower, more than we ever believe. As I will show you in a few slides, this is a process that can last more than 10 to 15 giga-years, which is more the age of the universe. The good thing is that we have a vast number of such systems in the universe. We see contact binaries and low mass and low temperature contact binaries everywhere in the galaxy, everywhere in all other galaxies. And usually these systems are combined with a third component, or they are within a multiple environment, like, for example, several studies that show that more than 60% of such binary systems are members of a multiple or a wider system. The challenge of the models become even more interesting if we consider that the contact binaries that we know so far is not well known for the, let's say, for the past 3-4 decades. The first contact binary was observed in 1903, so we have 120 years of knowledge of such systems. And only back in the 50s and 60s, we started to understand the geometry of a contact configuration. Back in the 90s, maybe early 2000, that is 2-3 decades ago, we started having the first statistical studies of 20-30 systems. Not a big number, but still these were the first attempts to understand statistically how this configuration can actually exist. The low mass contact binaries are the most frequently observed system with a common envelope. So among all the common envelope stars, the low mass systems are the most frequently observed. They are small in terms of size. They are solar type stars. They are actually main sequence solar type stars of the size of half a solar radius up to 2 or 3 solar radius. The mass is also from half a solar mass to 3 solar masses. The temperature ranges from 4,000 kelvins up to 6,000-7,000 kelvins at most. So we're talking about G, K, M spectral type. And they occupy the old population group of our galaxy, which is a very interesting information, because since they occupy the old population group, that means that the systems are very old. No matter that we're talking about main sequence stars of solar type, they occupy the old population group. That means, as I said before, this is a process that lasted for several giga years, although the system remained as main sequence stars. So the evolution of star system is totally different than the single star that we know from textbook. Since the configuration is contact, and we can describe the geometry easily with a Ross model, they follow certain empirical relationships. For example, the sum of the two radii is actually the distance between the two centers of the two components. And the distance of the two components is closely correlated with the orbital period from Kepler's law, and the orbital period with the size is closely connected with the mass and the radius, and eventually with the luminosity of the star. So all the physical parameters, mass, radius, luminosity, is correlated with the orbital parameters, which is the size of the stars and the orbital period. Having this in mind, back in 2006, I crossed into an idea, which was published 3 years later in 2009, to see how these physical parameters are correlated with the observational parameters that we directly see with our telescopes. For example, with photometry, we can easily derive the orbital period very accurately, down to a fraction of a second. With spectroscopy, we can derive the mass ratio from Doppler effect. So if you combine the orbital period, which is the parameter P in these equations, and the mass ratio, which is the parameter Q, we see that the systems, both the primary and the secondary components, blue and the red dots on all these 3 plots, are very closely correlated with the physical parameters, which is the mass, radius, and radii. That means we can extract empirical relations in order to derive the physical parameters directly from 2 observational values, the orbital parameter and the mass ratio, which is a direct consequence of the Ross geometry of the contact configuration itself. That means the question of why contact binaries is so interesting is self-explained. We can use the contact binaries as astrophysical tools because we can derive the absolute parameters, we can derive the absolute magnitude, and we can observe the apparent magnitude, and there we go. We have a distance modulus derived from a contact binary, like what we do for Cepheids and pulsating stars. These stars can actually be used as distance indicators, something that is well known from previous studies. Back in the 90s, we have several studies that proved contact binaries are very good distance indicators, and they were actually used for galactic distance calculations. There is an excellent opportunity that is in front of us to investigate evolution paths within a binary environment, and probably the evolution path towards merging events, that we don't know a lot of things about merging events that can be also extrapolated to other kinds of binary systems, not only in stellar main sequence stellar systems, but also in compact objects. Their parameters can be measured so accurately that even negligible orbital modulations can be monitored. So even a fraction of a second of the orbital period changes due to mass transfer, that means we can observe it, and we can extract information about the evolution of the 2 components individually. The orbital period modulations can actually studied and investigated through the O-C diagrams. The O-C diagrams is the observed orbital period minus the calculated orbital period of such a system. In other words, these plots show how the orbital period is changing over time. If we see a negative trend, negative parabolic trend on such a plot, that means that the orbital period is decreasing. That means that we have an evidence of a shortening of orbit that could be probably emerging progenitor. If we see a positive trend on the parabolic behavior of the O-C diagram, that means we have an orbital expansion, so the system is going to stop being a contact binary. In most of the cases here, you see that we have a periodic modulation. Maybe sometimes we have a periodic modulation on top of the parabolic one. The periodic modulation is an evidence of a third binary, probably a fourth binary, that we frequently observed in such systems. So the O-C diagram is a very good, actually it's an excellent tool to modulate, to investigate the orbital period modulations. Is this an evidence of merging? Well, this is an open question now, and this is what I'm studying in a project that I started 10 years ago in 2012. I will talk about this project in a few slides from this one. We're trying to understand how this negative trend in the parabolic behavior can occur. It can occur probably from angular momentum loss. It can be occur through magnetic braking. It can occur even from a gravitational wave radiation. But the systems, the components that consist contact binary is very slow in mass. So the magnetic braking, the gravitational wave is not sufficient to produce such an observed behavior. On the other hand, the mass transfer between the components and the angular momentum loss through the stellar wind is very well determined, and we can actually put constraints on the value of the angular momentum loss rate in order to understand how the system can actually merge or they expand their orbit. What do we know so far? The current model that we have so far is that for a given low mass contact binary, the progenitor could be a two-day detached system, two individual stars, main sequence stars with a two-day orbital period that eventually lose angular momentum, they come close to each other. Don't forget that this system might be within a multiple system, so the triple and the quadruple system can actually drag angular momentum out of the binary and force the binary to come closer to each other. But this angular momentum loss, in order to have a contact binary as we see it nowadays, is a very slow process. It takes more than 10 to 12 gigayears, even 15 gigayears to have a contact configuration if we start from a two-day detached system. Unless if we have a third component, let's say, that actually forces the contact binary to come closer due to mechanisms like the Gazeas mechanism that is well known even in a smaller scale, like in a planetary system. The components that we know so far, the components that we actually observe even spectroscopically for these contact binaries, we see that they are still main sequence. No matter if we're talking about a 10 or 12 gigayear old population, the systems are still main sequence components, and they belong to the old galactic population, as we said so far. The evolution is slow, so when they expand or they try to expand, they just fill the Ross lobes. So all this excess of mass just leave the system from the Lagrangian point 2, so we have angular momentum loss and mass loss from the system, and eventually they form a common envelope. They share thermal energy, and therefore they have similar surface brightness, which is something crazy if you consider that we have system with a mass ratio kind of 1/10. It's like having a basketball with a tennis ball next to each other, and these two stars with totally different mass, totally different characteristics, they have exactly the same temperature because they just share a common envelope with the same photosphere. This plot was one of the first plots that leads me to that three-dimensional plots and the Birken relations that you saw before. It is just a plot of the mass versus the orbital period, the logarithms of the orbital period. The black dots and the white dots are the primary and the secondary components respectively, and what you see is that no matter the orbital period of the system, the secondary component retains the mass between the values of 0 and 1. No matter how wide or close or short the orbital period is, the secondary component remains the same. The mass of the primary component, however, dominates this behavior. And what we see here is that all the systems have solar type characteristics from, let's say, half a solar mass up to 3 solar masses, as I said in the very beginning. The theoretical models that were produced by our colleague Gazeas at the University of Warsaw showed what I said before. For a 2-day detached system, when such a system loses angular momentum and they come, the two components come into contact configuration after several giga years, they end up in the contact configuration as we see them right now. What you see on these plots are the observational points from the previous plot that we saw. The observational points is what we see with our telescopes, orbital period and mass ratio, photometry spectroscopy, and the tracks are the theoretical tracks from the given model. You see apparently a perfect match, but in order to see a perfect match, it means that we gave a very specific value for the angular momentum loss rate and the mass loss rate from the Lagrangian point. That means in order to have such a model, we can put a very strict constraint on such evolution process, which is very good. But if you study this evolution rate, this evolution, the angular momentum evolution, we see that the time is longer than 10 to 12, even 15 gigayears, as I said before. The good thing is that from the observational point of view is that we have several sky surveys, we have ground-based observations, we have spaceborne telescopes that all put the data together. The ground-based observations are dominating now the well-detailed and studied systems, but the majority of them occupy the group of well-studied contact system, taking into account the combined photometric and spectroscopic solution. As I said before, for having photometry for the orbital period and spectroscopy for the mass ratio is the best thing we can have. And there are several active research groups around the world working on low mass contact binaries. In the parentheses you see, we have groups in Australia, Canada, China, Czech Republic, Greece, of course, Poland, Slovakia, etc. There are several groups working on these systems. On the other hand, we have spaceborne telescopes and global surveys, even sky surveys from space, providing ultra-high precision photometric measurements. So we have very well determined the orbital period, but they lack of high-resolution spectroscopy. This is still limited. We have low-resolution spectroscopy in some cases, which is sufficient for having temperature determination. And this temperature sometimes contradict with the color indices, which is another different story, how we can determine the temperature of a binary, of an eclipsing binary, when the light curve is variable, when the luminosity is variable. The good thing is that we have several global sky surveys from ground and from space, mostly from ground, because they provide long-term monitoring of such systems. In order to have temporal modulation studies on these physical parameters, we need to have long-term monitoring of these systems. So the small telescope networks have a huge advantage over the large facilities that cannot dedicate a lot of time on their studies of a single group of targets. So the lack of high-resolution spectroscopy apparently gives a limited information about metallicities, or it might be adequate only for temperature, but definitely we don't have sufficient data for radial velocity and apparently for mass ratio determination. So the models mostly are based on photometry. And this is a weak point in the study of eclipsing binaries in general. When we're based only photometry and we don't have the mass ratio as a secondary parameter, we don't have any information about the mass. We can assume the mass as a function of the inclination of the system, but we don't have the absolute value of the mass. So the lack of mass ratio results in wrong models in some cases, and only in totally eclipsing systems we are okay for, we can say that we have some sufficient solution and provide accurate results based only photometry. In some cases, and we have to be very careful when we see publications based on empirical relations. I see several, for example, publications based on my own empirical relations that I saw before, and they extract the physical parameters only with photometry, only with the orbital period, no mass ratio, for example. And if you see the physical parameters out of empirical relation, you have to be very careful if they are actually measured or they are calculated from empirical studies. And here we come in 2012, where I initiated the contact binaries towards merging project, COBITOM project, as I call it, which is an observing program that started here at the University of Athens as an observing campaign in order to gather as much information as possible for the long-term variability and the long-term monitoring and modulation of the physical parameter of such system. This project is closely connected with the WMA project that started back in 2002 by Professor Kreiner and Professor Rudzinski. And this resulted in the most detailed database of contact binaries globally as a combination of photometry and spectroscopy, because the WMA project provided high-resolution spectra and mass ratio for about 160 systems. We don't have a lot of systems with very accurately determined mass ratio. So this sample of 160 systems out of the WMA project is used in the COBITOM project nowadays in order to see small modulations of the physical parameters. If we come back to this diagram, the question that initiated the COBITOM project was, what is happening at the low end of the orbital period? What is happening when the system is so close to each other and the orbital period is less than 5 hours? And the second question is, what is happening at the lower end of mass when we have contact systems with components less than 0.1 solar mass? We have mass ratio even 15%, 0.15, or the record breaker is like 6%. The example that I said with the basketball and the tennis ball, imagine the tennis ball being even smaller. So we're trying to investigate with the COBITOM project, and this is the website that we have. One can visit us and see the collaborators, the telescope involved, and the publications that we have so far, in order to see what telescopes can actually contribute to the study, what is the need of long-term monitoring of the system, what is the target list actually, which are the progenitors of merging events that we are actually looking for. And this is an example of light curves, high-resolution photometry, and of course we have spectroscopy in the background on these systems. We always have and provide information in all optical bands, in all filters, B, V, R, and I. Sometimes we have clear filters, sometimes we have even in the mid-infrared information if we are lucky that other telescopes are observing different wavelengths. And this is an example of one of the very recent papers that we have, that one came in monthly notices last year. It's a sample of 30 systems. The systems are listed in the first column, the names. And you see that the second column provides the P3, which is the orbital period of the third component orbiting the binary. You see that the majority of the contact binaries have a third body. They have a third body orbiting. So the scenario that the third body dragged angular momentum from the contact binary and it forced the contact binary to come close to each other even faster might be true. As you see here, more than 60% of the system have a tertiary component. The next column is the amplitude. That means we have information about the mass of the third component. The next one is apparently the mass, the minimum mass of the third component. And I want to show you the last column, which is the P dot. This is the orbital period modulation of the contact binary. You see that the orbital period modulation sometimes have a positive or negative sign. That means that we have orbital widening or orbital shrinking. And this is mainly independent of whether there is a third body orbiting the binary or not. So this is still an open question. We are still investigating such system in order to understand why we have P dot, and this P dot is probably not correlated with the existence of the third component. So it's still an open question if the Gazeas-Lindow cycles actually play an important role in evolution of contact binaries. Taking into account the sample of the 30 systems that I showed you in the previous slide, we calculated the mass ratio. And the mass ratio is a very good indicator to study the stability of such systems. We have a Darwin instability criterion which says that when the ratio between the spin angular momentum and the orbital angular momentum is exceeding the value of 0.3, that means one is 3 times more than the other, then the system is unstable. All the systems that we studied, that means all the systems with very short orbital period, they have big enough mass ratio, and they lay down at the bottom right part of the diagram. These are the red stars of the plot. So the systems are very stable. That means, on contrary to what we believed, that the systems with very short orbital period, they are very close to be merged, this plot shows exactly the opposite. These systems are very stable, and the process is still very slow and probably to last for several more giga-years. So the next step in the Kopiton project now is the third paper that we're actually working on, that is to investigate the low mass ratio system. This is a work that is led by myself, and I have a PhD student, Sophie Palafuta, who is working on this project, and she's investigating how the extreme low mass ratio systems are actually have evidence of stellar merging scenario, which is not published yet, but we are soon going to show you our first results. So the future goals for observing such systems is to monitor ultra-short orbital periods in order to investigate the link between the third body and the orbital period modulation, is to observe also the ultra-low mass ratio systems in order to see if this is the right sample of contact binaries that actually can give us a red nova progenitor, and see through the Darwin instability criterion if the progenitor may lie between this sample, or directly observe the O-C diagrams and see the orbital period modulations and try to detect a red nova progenitor directly from the p-dot, from a big negative value of the orbital period modulation. So if we link all the above with the stellar evolution models, we can possibly expand this understanding of how these systems work with the possibility of hosting planets in the circumstellar or even the circumbinary material that exists around a common envelope star, detect the red nova progenitor and probably predict emerging events. That would be amazing. And of course, link the result of a merger, which is probably a fast-rotating star, with other fast-rotating stars and groups like blue stragglers or the KR coma type stars, which are very fast rotators, as we know so far. And these systems are not directly linked with each other. Maybe there is a link between them. So the current and future status of the study of contact binaries is that there is a need of dedicated ground-based and space missions focusing on high-resolution spectroscopy. We have enough photometry and very well-determined orbital periods, but we don't have spectroscopy, and this is something that we really need, and this is actually how an observing campaign can initiate and start gathering data from big telescopes and spectroscopic data. For the ground-based global surveys, we know that they play an important role in the time domain astrophysics with the long-term monitoring programs. And the long-term observing campaigns are essential for monitoring the negligible modulations, as I said, in the physical parameters. So small telescope, this is kind of a call, if you want to say, that small telescopes can actually collaborate. They can actually form global networks and even encourage the pro-am collaboration in data gathering in order to have all this information within a single database. So the ultimate goal in the Kopiton project and the overall study of the contact binary system is to study the ultimate fate of the low mass common envelope systems through the contact phase and the stellar merging process. So this was my talk, and I think that I gave you some big idea about how the contact binary studies nowadays, and what is the status of the study in these systems. And I'm open to your questions and your comments. Thank you very much for your attention.
Well, thank you very much, Kosmas. Very interesting talk. So we have time for questions. Let's see.
If there is a question, somebody can just open the microphone.
Yes, and ask the question.
We're not that many, so feel free to ask me.
Well, I have a couple of questions. The talk has been very interesting, but this is not, I'm not an expert on compact binaries. Well, you just mentioned about the need of a high resolution spectroscopy. Do you have any plan to observe this system with JWST?
Not with James Webb. Actually, we have several ground-based observatories of 3-4 meter class telescopes, and larger, of course, that can actually provide information for the mass ratio. We just need high resolution in order to see the Doppler effect. For James Webb, we need a lot of observing time. We cannot dedicate, James Webb cannot dedicate a lot of time to fully monitor one orbital period. We just need a few spectra out of that. So the best way is to ask for a ground-based telescope to take a single spectra within a certain phase of the orbital period, and then repeat it then and then and then by taking samples. And this is the strategy that we work nowadays, and we gather this year some observing time at the VLT. So we have an 8-meter telescope that can help us to provide some spectra, high-resolution spectra, but we don't dedicate the VLT for the entire night. We just need a single spectra, which is like 10 minutes of observing time, and these 10 minutes can be taken between 2 different projects.
Okay, thank you. Nice. And I was also wondering, when you mentioned about the orbital period modulation, I was wondering what is the sensitivity you need to detect, for example, the presence of a third body in the system.
I'm going back to the slide with the homogeneity diagrams. Where was that? Was it here? It was here. Yeah. The sensitivity in terms of what is the accuracy that we need, right?
Yes. Right.
When we observe a contact binary system and we calculate, even with the Fourier analysis, the orbital period, we can go down to a fraction of a second. We can actually have accuracy of 1/100th of a second in the orbital period determination. If we put all these values, let's say the orbital period this year or next year and the second year, you will create the homogeneity diagram like this. So you see on the top of each plot, you see the years. Even if you observe the system every 2 years, you can actually observe differences in the orbital period. This 1/100th of a second that I told you, it can be actually detected. In a long term, within a decade or even better, 2 decades, 3 decades, you can detect the trend of the orbital period modulation, and you can go back down to 10 to the -7 of a second. Yes. If it was from that plot, it was, no, where was the study with the 30 systems. I can show you the P dot. Actually, I want you to see the power. This is the P dot is this value times 10 to the -7 days per year. We can be that accurate by just simply calculate the orbital period as we simply calculate it with Fourier analysis. Right. So it's a simple question of the time domain astrophysics and the time series analysis that we do it as a textbook.
And And then I was wondering about, you said that maybe this system can host planets around the stars. So have you ever detected any planets around the system?
The simple reply is no. Well, we didn't detect any exoplanet orbiting a contact binary. We have some samples of exoplanets orbiting a binary system and not a contact binary. We have circumbinary planets, and sometimes we have circumstellar exoplanet within a binary system, but of course this is a detached system. Maybe it's a matter of accuracy that we don't see any exoplanet orbiting a contact binary. Maybe the exoplanet is hidden within a circumbinary material. For example, if we have a contact binary and a fuzzy circumbinary material around it, we won't be able to detect negligible fluctuation of the brightness because of an exoplanet. The fact is that we never observe an exoplanet around the contact binary. This might be the reason. Another reason might be orbital stability. There was a study that I did with a master's degree student of mine, and he studied the Kozai-Lindoff mechanism that showed that if there is an exoplanet orbiting a binary, this exoplanet doesn't have a stable orbit unless the exoplanet is far away enough. So it's also a matter of stability of the system.
Okay, thank you. And finally,
Hi.
Yes.
I'm Gloria. I'm from Barcelona. I have a question. Well, maybe it's a naive question. I come from the CV world, from binaries, but with a white dwarf or a black hole or some compact object. So I was wondering if you're assuming that these contact binaries are just two spherical bodies, deformated maybe because of the contact, or if there could be any other effect of asymmetric shapes or not so perfect that could then be detected in the modulation of the orbital period.
We definitely include the Ross geometry, so we definitely not treat them as spherical objects.
Yeah.
So we take into account the symmetries, of course, from the shape, following the Ross geometry, and we take into account the symmetries from the photospheric effects. For example, we have several photospheric spots that gives us symmetries on the light curve. So it's not like a sinusoidal wave. One peak, when you see, for example, the binary from one side, might be totally different from the other side because the other side might have spots. So these asymmetries are taken into account, and this can be explained from photospheric activity. And we are quite sure for that because we see across time modulation of the photospheric spots, because we see modulation of the asymmetries of the light curves. I don't know if you mean other kind of asymmetries in terms of a model.
Well, no, I assume that was the kind of model. I was thinking if there could be any other effect, like if that break so now the two stars are filling the Rauschlop, so maybe the geometry is mainly the Rauschlop surface, right?
Yes.
But if there is a third body or any effect that could break that into something more asymmetric.
Meaning
because you mentioned usually there are many cases where there's a third body. I was wondering if you have considered, or if it would be possible that these shapes are broken and then you observe some extra asymmetry in the orbits and changing also. Of course.
Yeah. I guess you assume that the third component is very close to the binary, that actually the gravitational attraction is prominent.
Yeah.
No, we didn't take into account such an effect, but I assume that if we have a third component that close, then the system is not anymore an hierarchical model, an hierarchical triple. It is a chaotic triple system.
Yeah. Okay. Okay, thank you.
We have time for one more question. If not, I have one, the last one, just a curiosity, because as I said before, you gave the name to an asteroid. If you can tell us about something about your discovery.
You should tell me in order to prepare a slide for that. What do you want to know about the asteroid itself?
When you discovered it, how it came about?
The asteroid was discovered back in 2000 with a telescope at the Lower Observatory. There was a project there at the Lower Observatory with a sky survey that scans the sky and finds minor objects. The project is called LONEOS, which is the Lowell Observatory Near Earth Object Survey. So LONEOS resulted with about 20,000 of small body objects in the solar system, mainly main belt asteroids. So all these 20,000 objects didn't have a name. So the International Astronomical Union started giving names following the research activity of researchers. So I was one of them, and was nominated with a name of one of these objects. The current asteroid that has my name now has a diameter of 5.5 kilometers. It's wide enough.
Yes.
But this is 17 magnitude object. Like, it's not easy to be observed with a small telescope. Yeah. And it orbits, of course, it's a main belt asteroid, and it orbits the sun within 3 years, if I remember well. 2.5 astronomical unit. It's one of the common asteroids that we have. The only extraordinary of this asteroid is that it has my name.
Well, this is good news.
Yeah, it's very, it's amazing and it's a big honor from the International Astronomical Union.
Yes. Well, congratulations.
Thank you very much. Thank you very much.
So, if there are no more questions, I think we can stop here. Thank you very much again to the speaker and to the participants. And thanks again for joining us. And see you next week with another seminar.
Thank you and good luck with your seminar talk program. And thank you very much for the invitation and for all of you for being here today.
Thank you very much.
Have a good evening.
Thank you. See you. Bye.